My name is Dionne. I'm a math student and a computer programming enthusiast. I also freelance from time to time, but mostly I do open source libraries. And today we'll be talking about metaprogramming. Actually, I will introduce what I claim to be a new paradigm for metaprogramming, a new paradigm that makes everything much easier and much more expressive due to C++14. So first out, I would like to introduce the different types of computations that we can do in C++, just to set, like the, just so you can see basically where we are going to live this presentation, like in which part of C++ we're going to dive. So first, there are runtime computations, the ones that you usually use at work, the ones that we all know, the first ones that we learn about. So in that world, we have runtime sequences, right? Like std vectors, std lists, std whatever. These sequences, they are homogeneous in the sense that they can only hold objects that all have the same type. So you can have a std vector containing ints. You can have a std vector containing strings, but you cannot have a std vector that contains both ints and strings, right? Unlike in some dynamically typed languages. Then we have runtime functions, which are just normal C++ functions. They operate at runtime. And then we have runtime algorithms to manipulate these sequences, and some of these algorithms can also take runtime functions, like higher order algorithms that take functions to modify sequences and stuff like that. So far, nothing new. Then, since C++11 and, well, C++14, mainly because of generalized const-expr, we also have const-expr computations, right? So this world is pretty much like the runtime world in the sense that everything is homogeneous, except if you are nice enough with the compiler, if you do not do anything nasty inside a computation. And by nasty, I mean like throwing, allocating memory, or stuff like that. So as long as you are nice enough with the compiler, you can ask the compiler to evaluate it at compile time, right? That is const-expr, basically. So in that world, we have const-expr sequences. We have const-expr functions. And we have const-expr algorithms, or we could have const-expr algorithms. They're not in the standard yet, but most of the algorithms in the standard that just manipulate iterators, there's no reason why we couldn't stick const-expr in front of them and they will work just as is. But so yeah, so in theory, we also have const-expr algorithms. It's just like not implemented in the standard yet. And now, the third quadrant. Now we're getting kind of funky, right? Heterogeneous computations. What does that even mean? So in that world, we have heterogeneous sequences. An heterogeneous sequence is simply a sequence that can hold objects with different types. Say std tuple is an heterogeneous sequence. And then we have heterogeneous functions, which is really just the fancy way to say, it's just a fancy name for template functions, really. It's nothing more than that, because a template function, when you think of it, it can take objects that have different types, and depending on which the type of the arguments, it's going to maybe return an object of a different type. So the return type can vary depending on the type of the arguments. And then we have heterogeneous algorithms. Or, yeah, well, we kind of do. So we don't have them in the standard, right? But it would make sense that we have them, just like const-expr algorithms, why not? But there is like a boost library that does that. But we don't have them in the standard. And of course, yeah, it's not that easy, unfortunately. So that brings me to my first claim, which is that we actually need algorithms to manipulate heterogeneous sequences. I think we need them because it simplifies a lot of metaprogramming tasks. It makes them almost as easy as writing normal, regular C++. I mean, this transform on a tuple is really not surprising to anybody here, right? Anybody who has written Python or Ruby understands that out of the box. It's very, very clear that we're going to call the function object toString on each element of the tuple. It's not surprising that the elements have different types. It just makes sense, and then we get back a tuple of strings. So I think we need them in the standard, or we need a good tool to do algorithms on sequences, on heterogeneous sequences. And then we have type-level computations. That is the fourth quadrant. Type-level computations, well, so in that world we have type-level sequences, which are basically sequences that can hold types. They can hold nothing more than types, so there's no like value associated to each types, due to each type in the sequence. And we have type-level functions, which are basically meta functions. That's all we call them, right? You probably know about type threats. Well, type threats are just an example of type-level functions. And then we have type-level algorithms to manipulate these type-level sequences with type-level functions, or meta functions. It's a bit clunky, but it works. And now let me make this other claim, which is that MPL is actually redundant. Why? My claim that I will try to demonstrate during this talk is that pure type-level computations are actually nothing but heterogeneous computations. So computations on tuples are strictly more general, strictly more powerful than type-level computations. And if we add a very good library to manipulate heterogeneous sequences, we could also do type-level computations with this library. Oh, God, that was OK. Yeah, now you saw everything. But the most important point, and I guess that is my third claim, is that C++14 is just like a huge game changer. It just changes everything when it comes to metaprogramming, mostly because of auto-deduced return type, generic lambdas. And generalized context is also nice, but only in the implementation of a library. It's not really useful as part of the interface, though. But yeah. So of course, this is just me claiming stuff, and I'm biased because some of you might know I authored a metaprogramming library recently. So yeah, I'm competing against these other libraries that I'm claiming they're less powerful. So just see for yourself. So this is all we use to check for a member. This is like the classical Sphene-based trick or idiom, or I would say hack, which allows us to check whether a type has a nested member called XXX. I won't even explain it because either you know it or you don't. But basically, this is just a trick of the language. You're able to know whether a type has some member, but it's a bit convoluted. Like when you see this for the first time, you're like, okay. Now soon in C++17, there would be this detection idiom using stud void t, and we're going to be able to make it much nicer, right? I think it's much nicer. It's less convoluted, and yeah, it's easier to explain to your coworkers, and it's better. But what I would really like to see is something like this. I want a one-liner for checking whether a type has a nested member, and I want it to look natural, and I want the idiom to be such that anybody who's new to C++ can say, oh, well, I really kind of understand what this does, right? And this actually works. I mean, this is completely possible with C++14. So now we're talking about, a one-liner for checking whether a type is a nested member, and it's it's also important to see that it's a variable, so it's a lambda, which makes it possible to declare it like in another function. You don't have to be at global scope or at namespace scope to declare such detectors. So it's much more flexible. Okay, introspection. So most of you probably already wished you could iterate over the members of a struct, right? A user-defined type. And not always easy to do it. We can use the Boost Fusion library to like adapt a struct into something that looks either like a tuple or a map, a compile-time map, where the keys are types, the types that are defined at the top of the slide. They're basically types, really. And then we can access these. These members, the members of the struct, using the types that are associated to them. Okay. Now with C++ 14, we can do better. We can use, instead of using like types that you have to declare beforehand, we can use compile-time strings for the keys. So this is an ugly macro, but basically what this does is create a compile-time string, and so you do not have to declare the members beforehand, the keys beforehand, which is very handy when you have 100 of them. And this is the future, where we have a user-defined literal that creates a compile-time string. You don't need to use a macro. It's super fast, compile-time, I mean, and it's super natural. And this is a GNU extension. It works. It could be in C++ 17 if the standard committee decides that it's worth it, and it's like trivial to implement. But for now, it's just a GNU extension. Yeah. Wow, this remote is getting crazy. I just press once and then it gets all crazy. Just a minute. Okay. Sorry about that. Okay. I am right there. Okay, now, how many of you have already tried to generate JSON for serializing or something like that? Most of you probably, yeah? Okay. So of course I'm not going to show how we used to do it because it might have been a bit nasty. But now it's pretty easy actually. So basically I'm really going to try to put this back on because it's annoying to, Okay. I wanted to be refunded for that. Okay. So now you just define the user-defined type using this macro here that provides some introspection capabilities. And then what we want is to be able to very simply say to JSON, print that, and it should give us that output. Good? Okay, so first up, we are going to handle base types. So whatever can be toStringed, we just do it. We want to quote characters. We want to quote strings. Nothing new. Then, if I receive a heterogeneous sequence, then I want to transform that sequence, just like std transform, right? No more complicated. Okay. So I transform that sequence, and then I call to JSON, so I get the JSON representation of each of the members, and then I join that with a comma, and boom. Then for user-defined types, like the one I just defined using the macro in like 2 slides ago, I transform the keys of that user-defined type, which are basically the names of the members of the struct. And I fetch the value of the member associated to that key, and then I just get the JSON representation of that member and do the obvious thing. And that's it. There's nothing more. And it works, and it compiles. OK. Now, maybe I found some cute examples that were like, wow, nice, everything works, and actually it doesn't work so well. So I'm going to give you a bit more. So error messages, yeah. Error messages, they used to be very, very, very nasty. Basically, you would just make a very little mistake, and then you get a big spew of very implementation-specific stuff. So for example, here, I'm calling MPL reverse on an integer. Of course, it's not going to work because it expects an MPL sequence. And I get something like, clear impl missing, blah, blah, blah. It's very clear to me because I know the MPL quite well. And I know that clear impl is just part of their type dispatching logic and blah, blah, blah. So I know exactly what this is. But most of you guys don't. And that's a problem. Whereas with static assert and other tricks, it's possible that, so if I do the same mistake, I can give you a very good error message and just say wait, well, 1 is not a sequence, and you try to call reverse on something that was not a sequence, so now it's pretty obvious. So I think that is helpful. Compile times, another thing that is quite problematic when we do metaprogramming. So this benchmark shows the time required just to include different metaprogramming libraries. I'm not doing anything. It's just like an empty CPP file, including these libraries. And of course, you can see that we are able to have much lower include times. And the reason why is just because the implementation inside of, like the implementation details of the library are so much simpler with C++ 14 than, the library is just smaller. We don't need to have like big preprocessor hacks, so this saves on the preprocessing time. And it's also easier to go with fewer dependencies, so we don't have to pull in many external dependencies to do what we have to do. So it's possible to reduce include times. Now this is the compile time performance of calling the transform algorithm on a tuple from the Hana library, a MPL vector and a fusion vector. And as you can see, the Hana tuple is slightly better. It's actually, it's much better than fusion, and it's slightly better than an MPL. It's still not satisfactory to me, but we're working on that. And the reason why a fusion vector stops at 50 is because you cannot create a fusion vector with more than 50 elements. It just blows up because of C++ 03 limits. Okay, so I think that we must rethink metaprogramming. I think that C++ 14 is such a game changer that it requires us to, we just have to rethink it from the base. It's not sufficient to just, put it like type name ... somewhere, and then variable templates, and then alias templates, and then const expr here, const expr there. It's not enough. We need to rethink the way we do it from the bottom. Of course, now the question is how we're going to do it. And well, of course, I'm here to talk, so here's my take. So most of you have probably heard of integral constant. I hope so. Basically, it's a wrapper for an integral value that's known, whose value is known at compile time, and we wrap it into a type because it makes it possible to manipulate it more with more flexibility. So the way we usually do compile time arithmetic is by defining meta functions. So this plus meta function here takes two integral constant x and y, and it just computes the integral constant whose value is the value of x plus the value of y. Simple. Simple, not pretty, but simple, and it works. And then, as you can see, I can just test that indeed integral constant in 1 plus 4 is just 5. It's okay, but not super awesome either, because of all these type name and colon type and stuff like that. There's a lot of syntactic noise, and it obscures what we're actually trying to do. So let us just try something for fun. And that thing is, well, how about defining this plus operator? Instead of defining it as a meta function, we could also define it as a template function which returns an integral constant. Okay? And the core, the very important point here is that we're returning an integral constant, not an integer, not the result of v plus u, really the result of an integral constant which contains the result of v plus u. That is really, really important. And then if we did that, we could eventually create integral constant objects instead of using the types as is. Just create the objects and then use the operators that we all know and love, right? And then since this plus operator returns an integral constant in something, and then this equal operator returns an integral constant in bool something, right? Because it compares two integral constants. Then you can take the decal type of that. It's like the type integral constant bool true or false. And then you can fetch the nested value in there. So yeah, this is an alternate way of doing compile time arithmetic. Is everybody following me at this point? No questions? Everything's clear as water? Yes?
I just thought, if you wanted to add two constants, you could just do constant expression, and the compiler is going to do that for you anyway.
Oh yes, okay, so the comment is that if you wanted to add, just let me know if I got it correctly. The comment is that if you want to add 1 plus 4, you could just do 1 plus 4, and then it's going to be a constant expression, and the compiler would say, well, I'm happy to compare 1 plus 4 equals 5 at compile time. Yes? That's a comment? Okay, yes, that's totally correct. And this is like a toy example, really, because in some other in some other context, you might get these integral constant int 1, integral constant int 4. They might be the arguments to a function, and then you don't know whether they are really like integers or compile time. You don't know whether they are compile time or not. And the only way really to do arithmetic in that context would be to use like the plus meta function that I showed earlier, or this technique. Like you wouldn't have the value of these integral constants until you fetch the column value of the nested thing, because that's what you receive as an argument. Am I being clear? So basically what I'm saying is that in this toy example, yes, of course it's equivalent. In other situations, it's just you just can't do it the other way around. Yes.
One key, right, is that there's a type associated with the value.
Yes. So the comment is that the key idea here is that there is a type associated with the value, right? So you can do a bunch of things also like overloading on the value of these expressions, whereas you cannot do it if you have just 1 plus 4. Okay. Of course, since the integral constants also provide a const_expr implicit Boolean const_expr implicit conversion to the nested to the inner value that they provide, then you can just drop the whole decal type column value thing. And this is, so basically, again, this whole expression is an integral constant bool something, right? It's an object of that type, but that can be converted to a Boolean const_expr. So we can just do that. And then we can use const_expr variable templates to make it a bit shorter. So we're just going to define, say, an integer int underscore c is going to be an integral constant int with that value. And then we can just drop, the length thing. So we're there. So now we've simplified, simplified the syntax quite a bit. And then the next step is to actually use user-defined literals, right? And then so I define a user-defined literal, and then I parse the content of that user-defined literal, which represents, a number, and I create the appropriate integral constant. And what I can do is just 1 underscore c plus 4 underscore c equals 5 underscore c. Now, if you go back to like a couple of slides ago and compare this with what we had, we have a huge gain of expressivity, really. I mean, this is compile time arithmetic. Yes?
Can you enlighten me why you used the .c version of the user-defined operator and not, let's say, the unsigned long for numbers?
Mm-hmm. Okay, so the question is, why are you using the char.dot version of the user-defined literal instead of, say, the unsigned long or something like that? The reason is that I want to create an integral constant type. So inside that function, I need to parse the value of the literal at compile time, right? So that, but at compile time, I mean, like so the type that is going to be returned by this operator, this user-defined literal here, is going to depend on the values of the c's here, right? Because it's an integral constant whose value represents what was, the number in the parameter pack. If I receive the value of that number as an argument, I do not know, because we do not have const_expr arguments, I do not know that this argument was const_expr, and the return type cannot depend on that. Is it clear for everyone? So basically, I need the value of my literal to be encoded in the type of in the type of my function. So I need to receive it as a template parameter, because the return type of that function is going to depend on the value of that number. Okay. Now let's see a real-world example. So we're going to compute the Euclidean distance in a 2D plane. This is the formula. This is what it looks like. Normally, I would have to define minus square root, brace yourselves, plus multiplies and stuff like that equal to, and then I just compute my distance. And it's a bit verbose, but it works very well. Now this is how we can do it now. We just have to use normal operators because, well, we defined, arithmetic operators on integral constants, so everything just works. Square root has to be implemented using, just normal operators too, which is much easier. And the key thing here is that I'm using auto, and that these guys are template parameters. Thing is that I'm using auto here because I cannot, because this is going to be an integral constant, something. It's not going to be like an int or a float or whatever. It's going to be an integral constant. So I need to use auto. And the type of this ys here is also going to be an integral constant. And my square root has to be written such that it can work with integral constants, but it's not like overly difficult. And then I just return. So the return type of square root is going to depend on the type, which is the type of this expression here. And I'm going to return an integral constant with the proper value inside it. But the real killer thing here is that since we only used normal arithmetic operators, this function also works with runtime values, right? Whereas the template that we wrote earlier doesn't work with runtime values. It's a template. It takes the integral constants as a template parameters. So it doesn't work with runtime values, whereas this one works with runtime values. And this is super cool. So the thing is, with this new way of doing computations at compile time using a normal value level C++, normal C++ syntax, thing is that you might have code right now that is written for doing meta computations and for normal computations, and this is the same code, and you could reuse it, right? But you don't know it because just of the way you decided to encode your type level computations. And this is not all. Once you start looking at integral constants as objects, you realize that you might want to improve their interface to do some funky things. For example, here I define a times member function, which is going to call, it takes a function and it's just going to call the function n times. So this allows me to do loop unrolling. So for those of you who have already done Ruby, this is pretty neat. So I just say 5 times f, and it just does 5 times f at compile time. So the loop is enrolled at compile time, which can be handy. But this is not really like, I'm not saying the standard integral constants should have that. I'm just saying like, this is the kind of things that we can achieve when we think out of the box for metaprogramming. It doesn't have to be ugly. It can be just very useful and very time-saving. Tuple access. So right now, we use studget to get the nth element of a tuple. Instead, we could define a operator bracket that takes an integral constant and just does studget with the value of the integral constant. And so that way we could use the bracket operator to access the members of a tuple. And which is like the nice thing with this is that say you had a vector, but you only accessed it using indices that are known in compile time, well, you could swap with a tuple and it would still work because they both define the same operator bracket operator. So as long as your indices are known at compile time, there is no reason why you shouldn't be able to access a vector and a tuple differently. And of course, why should we stop there? Stud ratio defines a quite ridiculous interface, if you ask me, for doing computations on compile time ratios, like stud equal, ratio equals, stud ratio plus, stud ratio multiplies, stud ratio divides, stud ratio, blah, blah, blah. I mean, it would be much simpler if they just defined the operators and it would be more natural. So this is actually something that we could maybe study and propose for standardization because it would just improve the interface by such a lot better. And it's actually so trivial to implement too that it's really worth it. Integer sequence, just the same. We could maybe have like a bracket operator to check the nth element of the integral of the integer sequence. Okay, now on to type threads because I claimed that we could also do type level transformations, and well, I need to show how to do that, right? So type threads, we add functions that take types and return types. So for example, I could define a add pointer meta function that just adds a pointer. This is equivalent to the stud add pointer in the standard. But now let's try to replicate basically what we did with integral constants, where we lifted the types to values. So instead of using integral constants as types, we use them as values. And instead of having meta functions to manipulate them, we now have functions. The way we do it is quite simple. We just define the type threads. So we define the dummy wrapper to all the types, okay? just like integral constant was a dummy wrapper to hold an integral constant, like an integer value that's known at compile-time. It was just a wrapper to hold that and to pass this around. Now we're going to do exactly the same with a different compile-time entity, types. And so I define a function that takes a type and returns a type, and I define a function that takes a type and returns like an integral constant. I can do this. And then you can create an object that represents a type, just call your function, which does the type thread on it, and that's it. So you have value level syntax, normal C++ syntax for doing meta computations, type level computations. Now you can go one step further and just define like a constexpr variable template. You don't actually save any typing, it's just for consistency in this talk. Okay, now why should we really want to do this? Well, since types are represented as objects, they are first-class citizens, which means that we can put them into tuples. Okay, we can also create a vector with types in it, but they would need to all represent the same type, right? Because you would say like stud vector type int, for example, and then you would just have like default constructed objects in that vector. So it's not really useful. You could, but it's really not useful. But where this is really useful is if you use a tuple, because now you can have different types inside your tuple. And so then you can just manipulate types as if they were normal objects. Now the full language can be used. So before, say you wanted to filter the elements of a type level sequence, you would need to use the kind of nasty MPL lambda expression domain-specific language to define your predicate. And now, since we are just manipulating normal C++ objects, there is absolutely no reason why we couldn't just write a normal generic lambda to do it. So instead of writing our predicate as a type level meta function or something like a MPL lambda expression, which basically is a hidden meta function, we can just write it very naturally using the normal C++ syntax. So what I'm doing here, this example, is really like I create a sequence which contains types, and then I just filter it, and I just keep the ones that are either a pointer or a reference. So this is a new tuple which contains type C char, and type C void footer. Now, again, since we are using the same syntax for type level and value level metaprogramming, we just need a single library to do it. So whereas we needed MPL and Fusion to achieve this before C++ 14, now we can achieve exactly the same thing using a single library. And as you will probably observe, the syntax is pretty much the same all the time. So it's easier to learn, it's easier to teach, fewer dependencies, and it just interprets like perfectly because it's actually just a single library. Now, the fact that we have a unified syntax means we can reuse more stuff. Like I said earlier with the compile-time arithmetic example, it's possible that some functions or some code that you wrote for normal C++, runtime C++ actually works with compile-time entities too, and you're just not aware of it. So what I did is I took Boost Proto, which is a very nice but also very complicated Boost library for doing expression templates. Of course, the library is complicated because the application is also quite complicated. And so I went into the tutorial and found an example there, which basically creates a domain-specific language, a very simple domain-specific language for creating arithmetic expressions. So this is something that basically represents, the first argument minus the second argument over the second argument. And the nice thing is that when I evaluate this expression and I pass it to compile time entities, it works. It returns an integral constant. And I can also, so it was originally written for runtime computations, of course, but it turns out that with like very, very little modification, it can also work with compile-time entities. And what I can tell you for sure is that when Eric Niebler wrote this library, he had no idea that I would sometime, come and just like put integral constants in there and it would work. Like he couldn't know it, right? It wasn't planned, but it just works because we're using the same syntax. This is really, really nice. I was actually very surprised that it worked. I was like, wow. I mean, I didn't think it was going to work, but then I was, oh, okay, I think we got something now. Again, since we have a single syntax for type level and value level computations, we can have more consistent code. So this is an example of creating a compile-time map with Boost Fusion, a heterogeneous map, sorry. So basically, you define the keys of the map here and the values of the map here, and it's not exactly obvious to someone who has never seen this code what it does. It's terse, but not exactly intuitive. And then you access the elements of the map using, the type to which they are associated. The syntax is slightly clunky. It works very well, but it's slightly clunky, and you have to know what you're doing. Whereas I think this is, while this is more verbose, it's also more obvious. You would expect to create a map using, a sequence of pairs, just like we do in the standard library, and then you associate types to, the value you want, and then you just use a bracket operator to get the value you want. Okay, I went quite fast. Now let us look at a case study. So this is a switch for boost any. The goal here is to create a switch which takes a boost any, and then depending on basically it's going to look at the dynamic type of the boost any, and it's going to dispatch to the proper function, right, inside the cases that I gave. And so if the boost any turns out to be empty, I want to get to the empty clause, and if nothing matches, I want to get to the default clause. So first, we want to make it really simple, so we're just going to use, we're going to define a case in this here. We're defining a case to be like a pair which associates a type to a function, okay? And then we define this default case here to be, we just defined a dummy type which represents the default case. And so case angle bracket default t is just going to be, like this function here, which associates default underscore t to whatever function you're going to pass to the lambda. And similarly to for empty. Now, here's what the switch looks like. So since I want to have this cute little syntax here, of calling a and then parens, and then boom, my cases, I'm going to have to return a function from this switch here. This is what I'm doing here. Switch returns a lambda, which takes the cases. Good. Then first so this lambda here takes the cases. Now a parameter pack is very nasty to manipulate if you want to do anything non-trivial. So I just put this in a tuple, and then we have all like fancy algorithms to manipulate tuples, just as we do with stud vector. So I'm going to find the default case, because the default case could be anywhere. So I'm just going to find the default case by saying, hey, each C here is a pair, right, which associates a type to a function. So I'm going to find the first one whose type is the default type, which is the dummy type that I said would represent the default case. And then, so I find the first one, the default case, basically. Now, findif here returns a compile time optional. It's like a stud optional or boost optional, except that whether it is empty or not is known at compile time. So then I static assert that I found the default case, because otherwise you messed up, right? So at compile time, it's going to tell you, you're missing something. I need to be exhaustive. And then I get the other cases. I just get the rest of the cases by filtering, by just keeping all the ones that are not the default case. Okay, filter here is like copyif. It's the same, except I really don't like copyif, the name. So, and then I unpack the rest of these cases into this generic lambda here, and I call impl, which I'm going to show you in a second. What unpack does is the same thing as to deploy, which is proposed like for the, I think it's the library fundamentals TS. But basically what it does is take a tuple and calls a function with the elements of the tuple. And the reason why I'm doing this is because I'm going to want to process the cases recursively using parameter packs, because in this case, it's the simplest way to do it. So I'm not advocating that you should use like tuples and algorithms on them all the time. Sometimes raw parameter packs are just the simplest way to go. Not all the time. All the time. So yeah. So here I use algorithms, and no more algorithms in there. So now let's dive into our result. Oh yeah, and so default arrow second here is because default is a compile-time optional, right? So I'm just fetching the second member of the pair, which is inside the optional. And I have the right to do it because I already static asserted that it contains something. And a type here is just like the runtime type information of the boost any, of like the element inside the boost any. So now I'm going to process cases. So, so there are two branches in the if. Let's ignore this branch here. So like if the type ID, of the case that I'm processing right now is the type ID of the, it matches the runtime type of the boost any, then I just do this, which I'm going to explain next. And then otherwise, I just, process the rest recursively. Very simple. I'm going to show you the base case, and then we'll come back. So the base case is when I'm empty, I just call the default case with no arguments. Okay? Now we're going back here. Okay. Okay, I got 15 minutes, so I'm really, okay. So basically, here I fetch the type represented by the type underscore C, okay? I actually didn't show you that because I thought we would be running out of time. But normally these like type objects, type angle bracket objects, have a nested colon type, okay, which represents the type that's in there, the T, so a type T has a nested colon type alias, which represents T. So when I get a case which is a pair which associates, a type angle bracket T to a function object, I can take the first member of the pair, which is a type angle bracket T, okay, and then they call type this object, which gives me the actual, type angle bracket T. And then I fetch the nested colon type, and that gives me the T in there. Is everybody following? So that's what I do here. And then, so if the runtime type of the boost any matches the T inside, the case, well, basically the type of that case, I run this, and otherwise, like I said, I just do it recursively. Now, if the type here is void, it means that I got an empty any. So I'm going to return from the if, not from the function. From the if, I'm going to return this lambda here, and otherwise I'm going to return this lambda here, and I'm going to call whatever lambda I returned with the case and the any. The reason why I'm doing this instead of using a normal runtime if is because if the type T here, so if my any is not empty, if I'm not currently processing the empty case, I cannot call the function with no arguments. So it's going to be a compile time error. So I need to make this call here dependent on something, so that the compiler only does syntactic analysis, but it doesn't actually try to call the function until it really needs to. So the thing is that this if here is takes a compile time integral constant, Boolean integral constant, and it's going to return this one or this one, And since the C inside this function is auto, the compiler doesn't know what is the type until I call it. But I'm never going to call it if it's not the empty any. Is everybody following me? Yes.
It's pretty much a static if, right?
So the comment is that it's pretty much a static if, and it is exactly a static if. Actually, I think I will change the name. So it's a static if, really. But the way to emulate, static if, which could be a language feature, but now the way to emulate it with the library is to make both branches, lazy by just making them lambdas, and then you return the branch and you do whatever you want with it. And then, so if it's not the default case, the empty case, then I just cast the boost any to the T, to the type that I'm currently processing, and then I just call my function with that type here, and that's it. Is everybody following? Awesome. Yes.
I do have one question. I noticed this is not part of class transfer, so it's the intent that this is a strictly generating runtime object. It's not going to be.
Okay. So the question is, or the comment is that so this function here is not const-expr, so the intent is that this can only work with runtime objects. And yes, indeed, it doesn't always make sense to to have all computations that working both at compile time and const-expr and non-const-expr because, for example, while boost any does allocations, the RTTI, the stud type index, we do not have this at compile time. So yeah, it only works with runtime objects. It wouldn't make any sense to have this const-expr. Yeah. Okay. So the base case, we already saw. So this is about like 70 lines of code. And your coworkers could understand it, mostly. And so this was actually based on like a presentation that was done at C++ Now by Sebastian Riddle. He's a very, very, very smart guy, but he didn't use a metaprogramming library, and his solution was, it had more features, but it was still much more, much longer and more complicated. So it really helps to have a metaprogramming library to help you with non-trivial tasks. And then when you are, actually doing something that's quite simple, like processing cases recursively, just drop the metaprogramming library. It's going to be a real pain in the butt to try to use it. So just do it recursively. But for the filtering, for finding something in a sequence, for doing that kind of stuff, it's very handy to have nice standard algorithm-looking tools. Okay, so now my proposal, and hopefully your deliverance from hard to do metaprogramming, is Hana, actually now Boost Hana, which is a library for heterogeneous and type-level computations. So it does everything that the MPL does, which is type-level computations. It also does everything that Fusion does, except it's not lazy, it's eager. So it's just for people who know Fusion very well. Everything in Fusion, in Hana, is eager instead of being lazy. Yes?
Sorry, I just want to go back to what we were just looking at. What's the approximate compile time for that usage sample?
I have no idea. I could look at it, but so the question is, what is the approximate compile time for this switch any sample? Maybe 1 second, but there are like many test cases in my because like all of this code compiles actually. The samples are taken automatically and put into my slides. So, but there are many unit tests. So maybe the file takes something like 1 second or so. There are a couple of unit tests. So yeah, it's really not that bad. It's much better than if you use another metaprogramming library, and it's much less complicated than if you rolled your own. If you rolled your own, it's depending on the complexity of the problem that you're trying to solve, it might be faster. It might compile faster than if you use, say, Hana, depending on the complexity of what you're trying to do. If you're trying to do something slightly complex, be assured that we are more clever than you in Hana, and that we make it like we are, the algorithm that we use are more optimized. But for very simple things, you might be able to, to have something that compiles faster because you don't even have the overhead of just including the library, which is like 0.3 seconds or something. So yeah, so it's quite fast at compile time. And I wasn't really clever actually in this implementation because as you see, as you might have seen, I find if and then I filter and then I unpack. There's like duplicate work here. I'm like going through the sequence, finding this case, and then I go again through this whole sequence filtering. I could have like partitioned instead. Partition the sequence into two different things, like a sequence that contains only the default case and a sequence which contains all the rest, and it would be probably more efficient. So yeah, but it was mostly for education here. So yeah, heterogeneous and Typelevel computations, although the heterogeneous computations for now are only eager, I'm planning on maybe adding views because there seems to be a need for it, but for now it's not there. There are more than 80 algorithms, most of which are highly optimized both for runtime and compile time. We are using pretty clever techniques, which I will have the time to show if I go a bit faster. And then there are about 8 heterogeneous containers, like a compile time map, a compile time set, a tuple, which is actually much more compile time efficient than std tuple, so you might want to change to it. And there is like also a compile time optional. There's a compile time string class. There is a compile time range, stuff like that. And so yeah, the compile times are much better. The runtime, the execution times are quite good. Also, they should be matching with those of Boost Fusion, which is pretty much what you would write, what you would achieve with unwritten code. It's working on C++14 compilers, which means only Clang, because even though GCC is supposedly C++14 compliant, it's full of bugs. So it's not quite working. And I mean, yeah. So it's almost there. There are a couple of bugs that still need to be fixed. I'm really looking forward for the GCC team to take my bug reports slightly more seriously and to be slightly more responsive. But apart from that, like we're really close. Maybe 2 or 3 bug reports left to fix, and we should be good for maybe GCC 5.3 or something. And other than that, well, it works on Apple Clang and Clang, non-Apple. Very, very fine. And MSVC, well, I'm sorry, guys. And yeah, so the good news is that it was accepted in Boost. I'm working very hard to make it part of the next release. Now, this is my homework towards you. So my homework towards you is to continue improving the library, to fix bugs when there are some, to work very hard so that it can be part of the next Boost release, to make this available and production ready as soon as possible for you guys. Your homework is to try it. Is to use it to file bug reports, submit suggestions so we can improve. And there's no library that's really good without having a large user base, which can really like say, hey, I need this, I need that I don't need. So we're gonna work together and build ourselves a very great metaprogramming library, which can be used to do some very interesting and very and things that would be very hard to do otherwise. So to finish up, I would like to invite you to embrace the future, the new C++14 standard and C++17, to try to keep your compilers up to date, to try to think out of the box, because as I hope I was able to demonstrate, it is possible to do some crazy, interesting things if you just think out of the box for a bit. It's been like 10 years that we've been like metaprogramming with angle brackets all over the place for like 10 years, and now I think it's possible to make this, part of the past. And also, obviously, since I wrote it, I would like to invite you to embrace Hana, because, well, I think this is really a library for the future of metaprogramming. And actually, I would even like, for some examples, for some ideas from Hana to be maybe ported to the standard, because I think some of these ideas are just no-brainers. Okay, I'm not saying like it's pretty functional library. Like programming functional library. The concepts come from functional programming. I don't want this in the standard necessarily. I'm not trying to force it like upon anyone. But some like just having a for each that works on tuple just makes sense for everybody. Okay, so thank you very much. so I have the time to take some questions, but I would also like to show, I would like to show some implementation techniques for those that want to see how this is actually done. Like, how can you filter a tuple? So any questions? Okay, go.
If you had to pick one or two language features that would make your life easier in this paradigm, what would you pick?
The question, if you had to pick one or two language features that would make my life easier in this paradigm, what would you pick? I want to be able to have a lambda appear in a unevaluated context, which means that I want to be able to say decal type some algorithm and then pass a lambda to this algorithm, and it still works. Right now, it doesn't work. I'm going to open a core defect for that. Richard Smith told me that it was that this restriction was now not required anymore, so this should work. The other thing that I want is a compile-time, compiler-generated closure. I want the tuple to be part of the language. I want it to be part of the core language. This way, we can have very, very compile-time efficient, optimally runtime efficient heterogeneous closure, and this is like this would be like the best feature ever. No, seriously, this would just make like long compile times mostly part of the past, especially if they give you like a way to access the nth element, so random access into your sequence as part, of the core language, then it would be just like super fast, probably. And yeah, so that would make a big difference. And apart from that, I think that's it, yeah.
Additionally, there are parameter path accesses coming through the core language.
So, yes, so the comment is that there are parameter packs, random access things that are being proposed. I do not like parameter packs because they do not compose very well. I think it is much cleaner to just stick your parameter pack into a sequence and then to manipulate it with algorithms. Because say you want to filter like a parameter pack with a predicate. How do you do that? You put the predicate first and then you expand the parameter pack into like into the list of the algorithm. It's just really clunky. Just like you wouldn't want to represent your state vector as some kind of magic syntax using ... It's just easier to put it in a container and then to pass it to functions. It just, yeah. How would you return a parameter pack? You can't. You can return a tuple. So I'm really not really fond of parameter packs. I would rather these kind of features not go into the language. Yes.
So you mentioned that compile time is a lot shorter with this approach than with the brackets and the explicit metaprogramming. So what do you attribute that? Why do you think that compile time is so much better?
Okay, so the question is, I say that the compile time is better with this approach than with, say, explicit angle bracket stuff and blah, blah, blah. So what do I attribute this speed up to? Actually, it's not faster. The reason why it's faster is because we can use so the fastest way to do pure type level computations is to go the dirty way and to do it like with the parameter packs and the old MPL way. It's faster, but it also makes you want to die when you write it. So the speed up is actually due to just other implementation techniques that we're using that are part of C++ 14. And this, I got some bonuses. I'm going to show it. But yeah, so actually the fastest way to do pure type level computation is not with this paradigm that I've shown you. But the most sane way to do it is definitely, yep.
Have you tried writing a switch for boost variant that does exhaustivity checking using Hana?
Have I tried to write a switch for boost variant which does exhaustivity checking with Hana? I haven't tried it. No, I think it wouldn't be much harder probably than writing the boost any switch, right? Because boost any is just a boost variant with unbounded types, like with unbounded possibility of types. Yeah.
Just on that, I think I wrote something like a type switch or counter matching. I have boost exhaustive checking for a variant, and I think we said it because I wanted to run under C++ 2015. Using Hana would have made it trivial.
Yeah, I was in your talk and I was thinking the same. Yep.
I've actually implemented the same thing, but without boost at all. It's actually very trivial to do. As long as you have 6+11, it's actually the only thing.
You mean the any switch or?
Not the any switch, but the variant switch on this variant is actually very trivial.
It could be. I'd like to see it. I'd like to see it.
I'll show you.
Okay. But I'm not sure it's more trivial than with the Hana way, right? Because you're still saving a lot of, you still have like algorithms to abstract some operations. Anyway, yeah. But in the case of a boost variant switch, it might not really be such a huge gain. Okay, so the session is over. If you still want to stay, I think we're going to cut the video, but don't do it if you don't want, because everybody's might be interested in seeing the implementation techniques. So you can leave if you want, but I'm going to show how to implement algorithms now. So basically, what we do is the goal is to always do the index computations with const_expr if possible, or to use std_index sequence to expand the parameter banks. So say you want to implement transform. What you can do is you take your tuple, you take your tuple, and then you take your function, and then you just compute the size. You just create an index sequence which contains a parameter pack of the size of the number of elements in the tuple, and then you call a helper function which has here these indices. And since this is a parameter pack going from 0 to n-1, where n is the number of elements in your tuple, you can just expand it and call f on each of the elements of the tuple that way. Okay? This is transform. Now, can somebody close the door, please? Okay, this is easy. You can implement other things with say for each or stuff like that using similar techniques, although somebody else is going to talk about that in a different session, so I'm not going to show it actually. But so now this is easy. Brace yourselves. Here comes filter. So filter is a nasty beast. Basically, okay, we're gonna do it step by step because this one is actually very difficult to implement. So we get a tuple, we get a predicate which contains which returns an integral constant. We just create an index sequence with the size of the tuple, and then what we're going to do here is we're going to use an helper to create an index sequence. Okay, and this index sequence is going to contain the indices of the objects for which the predicate returns true, and only that. Okay, and so this indices here again is an index sequence, a std_index sequence that contains only the indices where the predicate returns true. And then if we have such an index sequence, which I'm going to show you how it's implemented after, okay, but this is slightly nasty, but so once you have this, you can just slice your tuple using those indices, and slicing your tuple is just as easy as just get the proper elements, get the elements at the proper indices. Okay, so if we can actually get an index sequence here with the proper indices, we're good to go. Here, just so it's clear to everyone, I'm just like I said, predicate is returning an integral constant, Boolean integral constant, so I can decal type that, fetch the count value, do this for all the elements in the tuple, and right. So this is like this is n booleans, true, false, depending on the value of the predicate. Okay, let's go here. So filter indices is just this helper here. The real trick is going to happen in the filter indices helper here. Okay, so what happens is we create an array of the results, a const_expr array, okay? Then we use std_count, except like a const_expr version of std_count, but it's exactly the same. You just stick const_expr in front of std_count and it works. So we use std_count to count the number of elements that are true. Now, since this is const_expr, we're happy the result, we know what it will be the size of our resulting tuple. And then we compute the indices. So we are going to create an array which contains the indices of those elements that are true. This is pretty trivial. This is just normal C++ really. There's no Typelevel thing here or anything. So we just start the index at 0, and then whenever we find a result in the array that is true, we just say, hey, so the index of this true element is that, and we put that into the array. And now we create an array, a const_expr array, with the computed indices here. So here, this is a std array, a const_expr std array, which contains the indices of the elements that satisfy the predicate, and only that. What do we still need to do is, so the only thing that we still need to do is to put this into an index sequence. Yes?
Are you sure that the code in the if has I and current
What?
So indices is the result thing.
Indices is the result, yeah.
And the current index is how many indices you actually got.
Is the current,
The other way around.
no, it's not the, no, n is the number of elements in the resulting sequence, so I just fill my array, using I just fill my array using, wait a minute. Oh crap, I think that's right. It's really crazy because this actually compiles and works. Okay, so there might be a subtle bug here, but I think you get it that we're just basically filling the array. I didn't test enough, right? This is not the implementation in Hana. I just copy-pasted it and then simplified it, and I made a mistake doing it. So yeah, but basically what we're doing is just filling the array with the proper indices. And now, so assuming that I wrote my code correctly, this should be like a pseudo-array which contains the indices of the elements that I want to keep in the resulting sequence. Now, the only thing that's left to do is to put this into a std integer sequence. And the way we're going to do it is like this. So so this is just a nice trick to have a parameter pack from 0 to n here. And what I'm going to do is just create an index sequence using the computed indices, which is a const expr array containing the indices. So what I'm doing basically is I'm saying like I'm creating an integer sequence that contains the first computed index and the second computed index and so on. And since this inherits from std index sequence, I can use it in my slice here like this. So this is the way we do it. Yes.
Probably this is not possible, or maybe it's slower, but couldn't you just use something more traditional and fill out like an MPL list of indices, and if the predicate doesn't match, it's like a -1 index, and you exclude that when you expand the index sequence without having to deal with the
Okay. So the question is that wouldn't it be simpler or more or less efficient to instead use like a normal approach, recursive approach, to filter out the indices that do not satisfy the predicate? The thing is, no, because, okay, and actually, yeah. So the interest in this technique here is that there are no instantiations. It's just const expr homogeneous code. The compiler doesn't do any instantiations, right? There are no templates, there are no different types. If you recursively, look at the type list, you are like instantiating all those different types. So this is supposed to be much faster, and from the benchmarks I've done so far, it is also. So yeah, the interest here that we are doing all the heavy computation, the heavy index computation, we are doing it const expr homogeneous, which is quite fast. Okay, so that was it. I'm really out of time, so thank you.